This is a video for 6-5 day 2. So start the warm-ups, please, pause the video, and then come back to check your warm-ups, making sure you've got the skills and the formulas and the things from 6-5 day 1 that you need to be able to be successful in this. If you're back, okay, and if you're skipping this, that's the practice you really need to be proficient at this and up to date. So trapezoid rule would have gotten us a trapezoidal approximation of 80. Okay, I didn't ask you to, but I went and got the concavity so that we can see what's going on. And I went and found, not only, I found f, obviously we had f, its first derivative and its second derivative. And for the interval 0 to 4, its second derivative would be positive the whole time, or greater than 0 the whole time. So f is concave up from 0 to 4, so that trapezoidal approximation is too big. It's overestimating the integral's value. Simpson's rule, which will fit the curve a little bit better, Simpson's rule in two subintervals, got 64, and the exact value is 64 for the integral. So today we want to clean up some ideas about Simpson's rule, and we want to refine it, practice it a little bit more. It's not named for Homer Simpson, by the way. But in general, Simpson's rule is a better approximation than rectangles or trapezoids. If the curve is all linear, then obviously it's going to match, okay, because the curve isn't going to fit as well as maybe a straight segment that can calculate exactly. So that's why they're saying in general. Because Simpson's rule uses parabolas, it's exact if we are using this to find the integral of a polynomial function of degree 2 or lower. So if we tried this on a parabolic function, an x squared function, if we tried this on a linear function, it is going to give us the exact value. Okay, so any choice of how many subintervals, if it's a polynomial function, it's going to give us the exact value. N needs to be even because it's fitting it over a pair of 2 of our subregions. So let's try a little practice. The reason we need some of these techniques is not all expressions actually have an elementary antiderivative. And what elementary means to mathematicians is that it doesn't have an easy one. Now you and I would say, well, so what? That means there's just a harder one out there. There's a much harder one for some of them. So some of the math that we don't even really have or even have a great idea of, okay? That's what happens if you put the integral of e to the x squared into an integral calculator. It comes up with some math that mathematicians in research facilities and really, really high-end mathematicians do, very complex. Even Desmos can't graph what that would look like, what that integral's function would look like. So we need ways to then work with things that we can't get into that high-level math on, but we could still have a close enough estimate. As long as we know the estimate has a pretty low error in math, we can work with that. So exact answers aren't always available or even practical, and so math sometimes is willing to work with an estimate if they know it's got a very low error. We're realizing that Simpson's rule for curves has pretty low error. So if you're saying, are there other expressions that don't have what they call that elementary antiderivative? Yeah. There's others. So if you try to integrate sine of x squared, you run into that same problem. You'd run into some of that math that's pretty complex and high end, so you end up with some things that we're going to use approximations for because they'll be close enough. So the one we're going to work with is that first one. And we're going to try first to see how close we can get with trapezoid method. Then we'll see if we know if that's an over or under approximation. So to use trapezoid method, and we're going to split this into 4 subregions. Okay, so I started a table so that I can have those values that I'm going to need for trapezoid rule, because I'll need them again for Simpson's rule, so it's worth our time taking a moment and actually doing that. So if I break my integral from 0 to 2, that region, into 4 subregions, each subregion will be half in length along the x-axis, so e to the 0 squared is 1, because that's still e to the 0. E to the 1/2 squared will be e to the 1/4, so that's our value, no need to get all decimal here. E to the 1 squared is e to the 1, that's just e. E to the 3/2 quantity squared will be e to the 9/4, and this will become e to the 4th. So I have those values when I need to plug them in for my approximation, so take a second and get those. Then my trapezoidal rule, or my trapezoidal approximation for the area between the curve and the x-axis there, will be a half, because all trapezoids have half. Another half for the length of the subinterval from 0 to half, half to 1. And then we're going to put in all those heights, all those base lengths that serve as bases of our trapezoids. So the first one only serves once, 2 times for the second one, twice for the third one, so I should have 2 either, and the fourth one. But on that final 5th one, it only serves as the base of 1 trapezoid. And if you go calculate all that, our approximation for the value of that integral is about 20.645. We know that that's a pretty good estimate, but if this thing's really curvy, our trapezoid could do better. So let's see if we're over or underestimating what's going on there. So first derivative, f is e to the x squared, or first function. First derivative then, little chain rule, we've got 2x e to the x squared. And then we need product rule here. So you can trust me here. Second derivative is 2e to the x squared. You could get this, it's just product rule. That's the second derivative. And our interval was 0 to 2. So because I'm squaring that, e is going to be a positive number raised to a positive power. X squared is going to be a positive value, and I'm adding to that. So there's no chance of this actually becoming negative. F double prime is going to be positive, oops, greater than 0, for all the x's in our region, 0 to 2. Okay, even if I put in 0. Okay, and therefore, I'm going to get something that is an overestimate here because it's concave up. So F is concave up, 0 to 2. So our trapezoid, our value for t, overestimates. So our value for that's actually greater than what our actual integral value should be. Knowing that, we're going to switch over and use Simpson's rule then to approximate it because it is pretty curvy. So Simpson's rule should get us closer. With Simpson's rule, we're going to break it into 4 subintervals as well. So when we break Simpson's rule, we're going to get that the S that stands for Simpson's rule, that's not an integral. 1/3 is always in it. 1/2 is the length of each of our subintervals. And then we're going to use a lot of those same numbers, except we're going to use the first value once. We're going to use f at half 4 times. We're going to use f at 1 only twice. We're going to use f at 3/2 4 times. And finally, we're only going to use f at 2 once. And that comes to around that. Now, without making you go through and do this, if I had picked 8 subintervals instead, and you can see where that would get a little obnoxious and a little tedious, I would have come up with a Simpson's rule estimate of about 16.539. So that would be coming down a little bit. Remember, our trapezoidal estimate was 20-something, so we're already lower than that. And if you ask your calculator to actually get you an approximation, a numerical estimate of that integral, its estimate is around 16.453. So our Simpson's rule estimate was much closer. If we'd broken that into 16 subregions or 20 subregions, we would have gotten a lot closer, and for a lot of the applications, that close within a few hundredths would be an acceptable error to use that instead of the much more complicated math. So your assignment tonight is to do some more with Simpson's rule. And again, it's going to look a lot like last night's. So my suggested order is to do number 4 and then go do 16A. You're only doing the A parts on 16, 17, and 18. Then do number 5 and then go do 17A. Then do number 6, then go do 18A. Because they use the same functions and the same values, it will save you time. When it asks you to use the concavity, please demonstrate that you're using the function as your first value and then getting second derivative in order to determine the concavity by calculus.